August 1935, Nürburgring, Germany, the most demanding race circuit in the world. Rudolf Caracciola's Mercedes-Benz W25 Silver Arrow screams through the carousel corner at speeds that should be impossible. The banking throws lateral forces at the car that would tear apart ordinary suspension systems. The subsequent straight contains bumps and undulations that launch lesser cars airborne. Caracciolla's car stays planted. The suspension absorbs impacts that would bottom out competitors. The wheels maintain contact with the pavement through conditions that should cause catastrophic loss of control. In the pits, August Bilstein watches through binoculars. He's not watching Caracciolla's driving, brilliant as it is. He's watching the suspension movement. Specifically, he's watching the shock absorbers he designed, the ones nobody else has, the ones using technology that conventional wisdom says won't work. Those shock absorbers aren't filled with oil like every other damper in the world. They're filled with nitrogen gas under pressure, a radical design that German engineers had dismissed as impractical until Bilstein proved them wrong. 3 laps later, Caracciola crosses the finish line first. The Silver Arrow has won again. And buried in that victory, invisible to spectators and largely unknown even to other engineers, is a suspension technology that will revolutionize automotive engineering. But the story behind those gas pressure dampers isn't about racing glory. It's about a crisis in German industry, a technology that didn't exist when Germany needed it most, and an engineer who solved an impossible problem by ignoring what everyone knew was impossible. This is the story of how Germany in 1935 faced a suspension crisis that threatened everything from passenger cars to military vehicles. How conventional shock absorber technology couldn't be produced domestically at the quality levels German vehicles required, and how one company in a small German town created a completely new technology that worked so well it became the worldwide standard for high-performance suspension. Let me explain what a shock absorber actually does, because the name is misleading. Shock absorbers don't absorb shocks. Springs do that. Shock absorbers control springs. When your car hits a bump, the spring compresses, storing energy. That's good. It keeps the wheel from transmitting the full impact to the chassis. But springs don't just compress and stop. They bounce back, and they oscillate. Compress again, extend again, in a cycle that can continue for several seconds if nothing stops it. A car with springs but no damping would bounce down the road like a pogo stick. The oscillation would make the vehicle uncontrollable. You'd lose traction every time the wheel rebounded and lifted off the pavement. Shock absorbers, more accurately called dampers, resist this oscillation. They allow the spring to compress, absorbing the bump, but resist the spring's rebound, preventing oscillation. They convert the spring's stored energy into heat, dissipating it. The most common damper design in the 1930s was the hydraulic friction damper, a piston moving through oil inside a cylinder. As the piston moved, it forced oil through small orifices, creating resistance. The faster the piston moved, the greater the resistance, which is exactly what you want for controlling spring oscillation. This technology had been refined since the 1920s, primarily by British and American manufacturers. Companies like Monroe in the United States and Armstrong in Britain had developed reliable hydraulic dampers that worked reasonably well for passenger cars. Germany in the early 1930s had a problem. German vehicle manufacturers needed shock absorbers at a quality level German industry couldn't produce domestically. German passenger cars were increasingly sophisticated. The Autobahn system, beginning construction in 1933, would allow sustained high-speed driving that demanded better suspension. And the German military was rapidly expanding, requiring trucks and vehicles that could handle rough terrain. All of these applications needed reliable shock absorbers, and Germany was largely dependent on imports, primarily from Britain and the United States. This wasn't just an economic issue. By 1935, as Germany rearmed in violation of the Versailles Treaty, dependence on foreign suppliers for critical vehicle components was strategically unacceptable. The Nazi government pushed for autarky, self-sufficiency in strategic industries. The Reich Ministry of Economics issued directives. German vehicle manufacturers must use German components wherever possible. Foreign shock absorbers were acceptable only temporarily until German alternatives became available. But German alternatives weren't available. German manufacturers tried to produce hydraulic dampers domestically, but quality was inconsistent. Leakage was a chronic problem. Oil seals would fail, allowing oil to escape and air to enter. Performance degraded rapidly. Dampers that worked adequately when new often failed within months. The problem was partly metallurgical. Achieving the precise tolerances needed for reliable seals required manufacturing capability German industry was still developing. Partly it was materials. Seal materials and hydraulic oils with the right properties weren't readily available from German suppliers. German automotive engineers faced an uncomfortable choice: continue importing foreign dampers, politically unacceptable, use inadequate domestic dampers, technically unacceptable, or find a completely different solution. August Bilstein chose the third option. August Bilstein wasn't a household name, and his company wasn't a major industrial concern. Bilstein operated a small metalworking business in Ennepetal, a town in western Germany's industrial region. Founded in the 1870s, the Bilstein Company had traditionally manufactured window fittings, hinges, latches, hardware. It was skilled metalwork, but not particularly advanced technology. August Bilstein, who took over the company from his father, was competent but not prominent in German engineering circles. What changed Bilstein's trajectory was a combination of technical curiosity and economic necessity. As the Depression eased in the mid-1930s, automotive production increased. Bilstein saw opportunity. Window fittings were a limited market, but automotive components offered growth. He began studying suspension systems, reading technical literature, examining imported shock absorbers, and he noticed something that puzzled him. All hydraulic shock absorbers suffered from a fundamental problem: aeration. As the piston moved through the oil, it created turbulence. Air dissolved in the oil would form bubbles, cavitation, which made the damping action inconsistent. Worse, these air bubbles would compress under pressure, making the damper feel soft and spongy. Manufacturers dealt with this by using special oils, by careful design to minimize turbulence, by reservoirs that allowed air to separate from oil. But it was always a compromise. Air in the system was inherent to the design. Bilstein asked himself a seemingly absurd question. What if you eliminated the oil entirely and used gas instead? The conventional wisdom was clear. Gas dampers wouldn't work. Gas is compressible. Push on gas and it compresses easily. Oil is effectively incompressible. Push on oil and it resists. That resistance is what creates damping force. A gas-filled damper would compress like a spring, providing no damping at all. But Bilstein thought the conventional wisdom was missing something. What Bilstein realized was that damping doesn't require incompressibility. It requires resistance to flow through a restriction. In a hydraulic damper, oil is forced through small holes, orifices, or past valve edges. The viscosity of oil creates resistance to this flow. The faster the piston moves, the faster oil must flow through the restrictions, and the greater the resistance. But oil isn't the only fluid that has viscosity and creates resistance when flowing through restrictions. Gas does too, just less so. At normal atmospheric pressure, gas viscosity is so low that flow resistance is negligible. You can't make a damper from gas at atmospheric pressure. But what if the gas was under high pressure? At high pressure, say 300 psi or higher, gas behaves differently. Its density increases dramatically. And while it's still more compressible than oil, it's much less compressible than atmospheric pressure gas. More importantly, pressurized gas flowing through restrictions creates resistance. Not as much as oil, but perhaps enough. Bilstein began experimenting in 1935. His initial prototypes were crude, a piston and a cylinder filled with nitrogen gas at various pressures, with different orifice sizes to control flow. Early results were discouraging. At low pressure, under 100 psi, the gas compressed too easily and provided minimal damping. The piston moved almost freely, offering no control of spring oscillation. But as pressure increased, 150 psi, 200 psi, 250 psi, behavior changed. The compressed gas resisted piston movement more effectively. Flow through the orifices created measurable resistance. At approximately 300 psi, something interesting happened. The damper began providing resistance comparable to a hydraulic unit. The gas, compressed to roughly 20 times atmospheric pressure, had enough density that flow resistance became significant. Bilstein built test fixtures to measure damping force versus piston velocity. He compared gas dampers at various pressures to conventional oil dampers. Around 360 psi, the gas damper's performance curve roughly matched a typical hydraulic damper. But there was an unexpected benefit. The gas damper's performance was more consistent. With no liquid to slosh around, no air bubbles to compress, no temperature-dependent viscosity changes, the gas damper provided steady damping regardless of how it was oriented or how hard it was worked. There was also a problem. The gas wanted to escape. A gas damper at 360 psi has that pressure trying to escape past the piston rod seal every microsecond. Any leak, any imperfect seal, and the pressure drops. As pressure drops, damping decreases. A leaking gas damper fails catastrophically. It doesn't just perform poorly, it stops damping entirely. This was the challenge German manufacturers had struggled with in conventional hydraulic dampers, achieving reliable seals. For a gas damper at 360 psi, the sealing requirements were far more demanding. Bilstein's solution combined several technologies. First, floating piston design. Instead of a single chamber containing gas, Bilstein used a two-chamber system. The main chamber contained hydraulic oil with a damping piston. A secondary chamber contained pressurized nitrogen. Separating the two was a floating piston, free to move but sealing gas from oil. This meant the piston rod, the part that moved in and out, only had to seal against oil, not high-pressure gas. Oil is easier to seal than gas. It lubricates the seal and doesn't penetrate as easily. The high-pressure gas in the secondary chamber pushed on the floating piston, which pressurized the oil in the main chamber. This kept the oil under pressure, preventing cavitation and air bubble formation. Second, precision manufacturing. Bilstein invested in precision machining equipment. The piston rod needed to be perfectly straight and smooth. The cylinder bore needed to be precisely sized and finished. Tolerances were measured in thousandths of a millimeter. This level of precision was unusual for shock absorber manufacturing in 1935, but it was achievable with careful work. Third, advanced seal materials. Bilstein worked with German chemical companies to develop seal materials that could withstand the pressure and temperature cycles. Early synthetic rubbers and composite materials were emerging from German chemical industry. Bilstein was an early adopter. Fourth, quality control. Every damper was pressure tested. If it lost pressure over 24 hours of testing, it was rejected. This rigorous quality control meant higher production costs, but also meant that dampers that left the factory would perform reliably. By late 1935, Bilstein had working prototypes that demonstrated reliable performance, but proving they worked in a laboratory and convincing customers to trust a radical new design were entirely different challenges. Bilstein needed credibility. He needed to demonstrate that gas pressure dampers weren't just a theoretical curiosity, but a practical improvement over conventional technology. Racing was the obvious venue. Motorsport pushed equipment to extremes, and success in racing conferred prestige that translated to commercial acceptance. Bilstein approached Mercedes-Benz, whose Silver Arrow race cars dominated Grand Prix racing. Mercedes engineers were skeptical. They had perfectly good hydraulic dampers from British suppliers. Why risk a radical change? Bilstein's pitch was simple. Test them. No commitment, just testing. If they don't work better, you've lost nothing. Mercedes agreed to test gas pressure dampers on practice cars. The results got their attention. The gas dampers provided more consistent performance over long runs. Hydraulic dampers would fade as oil heated and thinned. Damping force would decrease after hard use. Gas dampers showed minimal fade because gas viscosity changes little with temperature. The gas dampers were lighter. No reservoir of oil meant less mass. In a race car where every kilogram matters, this was significant. And the gas dampers seemed to keep tires in better contact with the road surface, especially over the Nürburgring's notorious rough sections. The consistent damping, without the sponginess that aeration caused in hydraulic dampers, meant more predictable handling. Mercedes fitted Bilstein gas pressure dampers to Rudolf Caracciola's car for the 1936 Eifel-Rennen race at the Nürburgring. Caracciola won convincingly. While nobody attributed victory solely to shock absorbers, Mercedes engineers noted improved suspension performance. More testing followed. By 1937, Mercedes Silver Arrows were using Bilstein gas pressure dampers as standard equipment. Auto Union, Mercedes' main German competitor, followed suit. The racing success gave Bilstein credibility, but it also caught attention from another quarter, the German military. The Wehrmacht, Germany's rapidly expanding military, needed vehicles. Trucks, staff cars, reconnaissance vehicles, everything from motorcycles to half-tracks. And all of them needed suspension systems that could handle terrible roads, cross-country travel, and sustained abuse. Military vehicles put extraordinary demands on shock absorbers. A truck loaded with ammunition or supplies traveling on unpaved roads, absorbing constant impacts. Dampers failed regularly. The Wehrmacht logistics officers reported that shock absorbers were among the most frequently replaced suspension components. Imported British dampers worked well, but were expensive and subject to supply disruptions. Domestically produced hydraulic dampers were cheaper, but less reliable. Neither was ideal for military applications. The Wehrmacht's technical procurement office heard about Bilstein's gas dampers through the racing successes. They requested testing on military vehicles. Tests began in 1937 on Opel Blitz trucks, the standard Wehrmacht medium truck. Bilstein dampers were fitted to test vehicles and run through punishing trials, sustained high-speed road travel, cross-country over rough terrain, loading with maximum cargo weight. Results were impressive. The gas dampers outlasted conventional hydraulic units significantly. A typical hydraulic damper on a loaded truck might last 15,000 to 20,000 kilometers before requiring replacement. Bilstein gas dampers were still functioning well after 40,000 kilometers. Failure modes were different too. Hydraulic dampers degraded gradually as seals wore and oil leaked. Performance slowly decreased until they were useless. Gas dampers either worked or they didn't. Seal failure meant rapid pressure loss and immediate failure. But properly manufactured gas dampers with good seals simply didn't fail under normal use. By 1938, the Wehrmacht began specifying Bilstein dampers for new vehicle procurement. This provided Bilstein with massive production contracts and forced rapid expansion of manufacturing capacity. In 1935, Bilstein employed perhaps 50 workers, producing window fittings and small quantities of experimental dampers. By 1939, the company employed over 500 and was producing thousands of gas pressure dampers monthly. This expansion required solving production challenges. Nitrogen supply. Each damper required a nitrogen charge. Bilstein needed reliable nitrogen supply in industrial quantities. They partnered with Linde AG, a major German industrial gas supplier, establishing procedures for controlled gas filling. Precision manufacturing at scale. Making a few perfect dampers in a laboratory is different from making thousands per month in a factory. Bilstein invested heavily in machine tools, training, and quality control systems. Component supply. Bilstein needed high-quality steel tubing for cylinders, precision-ground rod stock for piston shafts, seal materials, fittings. They developed relationships with German steel mills and chemical companies, sometimes working with suppliers to develop materials to Bilstein specifications. Testing capacity. Every damper needed testing. Bilstein built automated test rigs that could cycle dampers thousands of times while monitoring performance and checking for pressure loss. The German government, recognizing Bilstein technology as strategically important, provided support. Bilstein received priority allocation of materials. Workers were exempt from certain military draft requirements to maintain production. By 1940, Bilstein was producing dampers not just for passenger cars and trucks, but also for military vehicles, including half-tracks, scout cars, and even some tank applications. Between 1935 and 1945, Bilstein continuously refined the gas-pressure damper design. Improved seals. Working with German chemical companies including IG Farben, Bilstein developed better seal materials. Early synthetic rubbers gave way to improved compounds with better temperature resistance and longer service life. Optimized valve design. The orifices and valves that controlled gas flow were refined through testing. Bilstein developed velocity-sensitive valving, small holes for low-speed movement, providing compliance for small bumps, larger holes opening at higher piston speeds, providing stronger damping for large impacts. Adjustable damping. Some applications benefited from adjustable damping force. Bilstein developed designs with external adjustment mechanisms that changed orifice size or gas pressure. Specialized applications. Bilstein created dampers optimized for specific vehicles. Heavy trucks needed different characteristics than sports cars. Military half-tracks needed different specifications than passenger sedans. By 1940, Bilstein held numerous patents on gas-pressure damper technology. The fundamental concept, using pressurized gas for damping, couldn't be patented. It was too basic. But specific implementations were protected. During World War II, Bilstein production was almost entirely military. The company made dampers for Wehrmacht trucks, Opel Blitz, Mercedes L3000, others. Military cars, Cuba wagon, Schwimmwagen, half-tracks, scout cars and armored cars, and some tank applications, though tanks used torsion bar suspension with simpler dampers for most applications. Production peaked around 1943, with several thousand units per month. This was substantial, but still a fraction of German military vehicle production. Not every vehicle received Bilstein dampers, particularly as the war situation deteriorated and resource shortages worsened. Allied bombing targeted German industry extensively, but Bilstein's facilities in Ennepedo were not major targets. The town's relative obscurity and the small size of Bilstein's operations compared to major industrial centers meant they escaped the worst of the bombing. However, raw material shortages affected production. High-quality steel became scarce. Seal materials were increasingly substituted with inferior alternatives as German chemical industry struggled under strategic bombing and material shortages. By 1945, production had declined significantly as overall German industrial capacity collapsed. After Germany's surrender in May 1945, Bilstein's facilities were in the British occupation zone. The company faced an uncertain future. Military contracts ended instantly. German automotive industry was devastated, and the occupying forces were initially hostile to German industrial enterprises. But Bilstein had assets, intact manufacturing equipment, surviving engineering staff, and a technology that was still advanced by global standards. The Allied forces needed vehicles. Their own trucks and cars, driven hard during the war, needed maintenance and repair. Some Allied officers examining German vehicles noticed the Bilstein dampers and asked whether they could be repaired or replaced. Bilstein, seeking any business to survive, began producing dampers again, initially for Allied vehicles, then for the slowly recovering German civilian market. The real breakthrough came in the early 1950s as Germany's economic recovery accelerated. German automotive manufacturers, Volkswagen, Mercedes-Benz, Porsche, BMW, resumed or began production. All of them needed suspension components. Bilstein's gas pressure damper technology, which had seemed radical in 1935, was now proven. 15 years of development and millions of kilometers of use had demonstrated reliability. German manufacturers increasingly specified Bilstein dampers. Racing provided visibility again. As European motorsport resumed in the late 1940s and early 1950s, Bilstein supplied dampers to race teams. Success in racing, particularly in demanding events like the Mille Miglia and Carrera Panamericana, established Bilstein's reputation beyond Germany. Through the 1950s and 1960s, Bilstein expanded internationally. They established relationships with foreign automotive manufacturers, initially in Europe, then worldwide. The technology that Germany developed out of necessity in 1935, because they couldn't make conventional hydraulic dampers reliably, became recognized as superior to conventional designs for high-performance applications. Gas pressure dampers offered advantages: consistency, no aeration, no fade, predictable performance regardless of temperature or use intensity, durability, proper seals and quality manufacturing meant long service life. Performance, the pressurized oil prevented cavitation, allowing dampers to control suspension more effectively, especially under hard use. Tunability, gas pressure could be adjusted, valve designs could be optimized for specific applications. By the 1970s, Bilstein was supplying dampers to premium automotive manufacturers worldwide. Their distinctive yellow paint, adopted in the 1950s for brand recognition, became associated with high-performance suspension. Other manufacturers developed gas pressure dampers, some under license from Bilstein, others using their own designs. The technology that August Bilstein developed in a small German town in 1935 became standard in everything from sports cars to SUVs to racing vehicles. The Bilstein story illustrates a pattern that recurred throughout German industrial development in the 1930s: necessity driving innovation. Germany's post-World War I situation left the country industrially capable but resource-constrained and internationally isolated. This forced German engineers to find alternative solutions to problems that other countries solved by importing materials or technology. Sometimes this led to dead ends. German synthetic rubber, Buna, was inferior to natural rubber, for instance. But sometimes it led to innovations that proved superior: Bilstein's gas dampers, German jet engines, certain chemical processes. The irony is that Bilstein's innovation, developed partly to reduce dependence on British imports, eventually became a technology Germany exported worldwide. Modern automotive suspension owes much to Bilstein's 1935 innovation. The principles August Bilstein worked out, pressurized gas preventing cavitation, floating pistons separating gas from oil, precision manufacturing for reliable seals, are still fundamental to high-performance damper design. Subsequent developments refined Bilstein's concept. Remote reservoir designs placed the gas chamber separately from the main damper body, connected by a hose. This allowed larger gas volume and better heat dissipation. Position-sensitive damping used damper position, how far compressed or extended, to vary damping force, not just piston velocity. Electronic control allowed active adjustment of damping based on sensors reading road conditions and vehicle dynamics. But all of these are refinements of the basic gas pressure monotube damper design Bilstein created. August Bilstein died in 1970, having lived to see his company become a global leader in suspension technology. The small metalworking shop that once made window fittings had grown into an international corporation with thousands of employees. Bilstein never achieved the public fame of automotive pioneers like Ferdinand Porsche or Fritz von Opel. His innovation was invisible, literally hidden inside vehicle suspensions, and too technical to capture the public imagination. But engineers knew. The Bilstein name became synonymous with high-quality dampers. Automotive enthusiasts learned that yellow Bilstein shock absorbers meant serious performance suspension. The company remained family-controlled for decades, with August Bilstein's descendants continuing its management and preserving the engineering-focused culture that defined its early success. In later decades, Bilstein became part of the German industrial conglomerate ThyssenKrupp, yet the brand and engineering culture endured. Today, Bilstein remains headquartered in Germany and is recognized worldwide as one of the most respected names in suspension engineering. The next time you see a shock absorber on a car, a motorcycle, a mountain bike, there's a good chance it uses gas pressure technology descended directly from Bilstein's 1935 innovation. If you've ever driven a car with performance suspension, felt it absorb bumps smoothly while keeping tires planted, you've experienced the benefits of pressurized gas damping. This technology exists because Germany in 1935 faced a problem. They needed shock absorbers they couldn't make using conventional methods. August Bilstein solved it by doing what everyone said wouldn't work, using high-pressure gas instead of oil. And in proving the skeptics wrong, he created a technology that became the worldwide standard. That's not just a story about engineering. It's a story about the value of questioning conventional wisdom, about solving problems by ignoring what everyone knows is impossible. Germany had no adequate shock absorbers in 1935, so Bilstein created gas pressure dampers instead. And they work so well that 85 years later, we're still using the same basic technology. That's knowledge you now have.